Your instinct is telling you a very comfortable lie about what's up there. It says there's a campfire, a gigantic campfire, burning in the middle of the darkness, just like firewood burns on a cold night, only much bigger and much farther away. The problem is that fire has a recipe, and the recipe is short: heat, fuel, and oxygen. Without oxygen, the flame doesn't weaken slowly, it dies in the very same second. Any child who has ever covered a candle with a glass has seen this happen. And space has no oxygen. There's no air, no atmosphere, not a single loose molecule floating around to sustain a flame. The void between the earth and the sun is the most sterile place that nature can produce. So there's one question left that almost no one asks out loud. If the sun is hanging in that void with no oxygen at all, how has it stayed lit after 4,600,000,000 years? The answer that most people carry with them their whole lives is that the sun is a huge ball of fire. And that answer is false. It's not a didactic simplification. It's not a useful half-truth for children. It's false in the literal sense. The sun is not burning, and it never has. What happens inside is something else. And that other thing is much stranger than fire. It involves a particle passing through a wall that it doesn't have enough energy to cross. It involves a nucleus that, by the numbers, is too cold to work, and yet it works anyway. And it involves light so old that, when it began its journey, there was no one on Earth yet who could look up at the sky and ask, why? I'm going to show you these three things in order. And before the end, I want to get to a number that took me a while to accept. Per kilogram of matter, your body produces more heat than the sun. This comes from a simple division, and the result's correct. Two objections usually come up here, and both are reasonable. The first is about scale. Maybe the sun is just ordinary fire, only gigantic, and its size explains its duration. This explanation doesn't hold up to even half a page of calculations, and I'll do that calculation in a moment. The second one is better. Maybe the sun carries its own oxygen without needing oxygen from space. And it really does. Oxygen is the third most abundant element in the star. That doesn't help at all, because in the center of the sun, no oxygen atom holds on to its own electrons. And without electrons in the shell, no chemical bond is possible. The ingredient is in there, present and useless. It's worth starting with fire, because almost no one really knows what fire actually is. When a candle burns, nothing fundamental is happening. The atoms remain the same. Carbon is still carbon, hydrogen is still hydrogen. What changes is just who is holding hands with whom. The paraffin molecules break apart. The oxygen from the air takes its place, and the atoms rearrange themselves into a slightly more stable combination. The difference in energy between the old arrangement and the new arrangement escapes as light and heat. That's what fire is, a swapping of partners between atoms, a reorganization of electrons in the outermost shell, the one that atoms use to interact with their neighbors. The nucleus, where almost all the mass resides, doesn't even notice that the candle exists. It goes through the entire burn untouched. There's a difference between fire and the sun that any kitchen reveals for free. A candle flame has a tip, and the tip points upward. It has this teardrop shape because hot air rises and pulls the flame along, which means the shape of fire is made by Earth's gravity. In free fall, weightless, a candle flame turns into an almost perfect blue ball, and this has already been filmed in orbit. The sun is also round, but for a completely different reason. Its gravity pulls equally in all directions, and up there is no up. The color gives away the rest. The orange color of the candle indicates a temperature around 1,000 to 1,400 degrees, while the surface of the sun goes beyond 5,000, and that's why its light appears white. That's the weak part of the story. A chemical reaction affects the outside of the atom, and the outside of the atom holds very little energy. If it were possible to break apart the nucleus instead of the shell, the energy released would be about 1,000,000 times greater, Not 30 times more, not double, but 6 orders of magnitude. 19th century physicists did a calculation that scared an entire generation. If the sun were made of the best coal, with plenty of oxygen constantly supplied, how long would it last burning at the intensity we observe? About 5,000 years. 5,000 years is just a little more than the age of the pyramids. If the sun were fire, it would have gone out before any human civilization recorded the first word in clay. The light that illuminated the construction of Giza would have already faded halfway through. So, the sun couldn't be coal. There was a second, more elegant hypothesis left. Maybe the source of energy was gravity itself. A ball of gas that size, slowly shrinking in on itself, releases heat in the process, for the same reason that a tire pump gets hot in the hand of the person pumping. Compressing gas always heats it up. With this mechanism, the sun converting weight into heat would last for about 30 million years. 30 million seemed reasonable. It even seemed generous. But at the same time, geologists were hammering away at layers of sedimentary rock and coming up with a completely different number. The rocks required hundreds of millions of years to form, and the biologists needed even more time than the geologists. The Earth was older than the sun. According to the physics of the time, the planet was older than the star that illuminated it. No rounding error explained that, and no technical detail did either. Physics said one thing, and the Earth said another, with the layers of rocks stacked there as proof. This part of the story is the one I like the most, because it shows that science doesn't move forward when someone finds a pretty answer. It moves forward when two pretty answers refuse to fit in the same world. The solution appeared in 1920 at a meeting of British scientists in a talk by an astronomer named Eddington. He proposed something that at the time sounded almost mystical. The sun's energy didn't come from chemistry or gravity, but from inside the atoms. Hydrogen turning into helium with a tiny fraction of the mass disappearing along the way and becoming pure energy. In the same speech, he said that anyone who thought that was too hot to be true should look for a hotter place to spend eternity. He was right, and it took almost 20 years for someone to prove in detail how that worked. Before getting to that detail, there's a hurdle we need to clear, and it's much stranger than it seems. No one knew what the sun was made of. Until the mid-1920s, the dominant opinion among astronomers was that the sun had more or less the same composition as the Earth. Iron, silicon, magnesium, a very hot and very large ball of molten rock, but chemically familiar. In 1925, a young astronomer named Cecilia Payne submitted a doctoral thesis that said something different. She applied a new theory about how heat affects the light that atoms emit, and the result was always the same. The sun was made almost entirely of hydrogen and helium. The heavy elements appeared in ridiculously small amounts. The senior astronomer who reviewed the work found the result impossible and asked her to include a sentence saying that number was almost certainly spurious. She included it. 4 years later, the same astronomer reached the same conclusion by another route, published it, and the idea went down in history under his name for a long time. I can't tell this part without some bitterness. The most important discovery anyone made about the sun in the 20th century was printed with a warning that it was probably wrong, written by the person who was actually right. And hydrogen changes everything. It's the simplest atom that nature can assemble. Proton in the middle, electrons spinning around it, and nothing else. It's also the overwhelming majority of ordinary matter in the entire universe. There's hydrogen in the glass of water you drank today, 2 in each molecule, and they're exactly the same atoms that are being consumed in the center of the sun right now. The fuel is the same, and the only difference is the pressure. So, the story begins in a cloud. Billions of years ago, in the place where the solar system is today, there was no star at all. There was a huge cloud of gas and dust, cold, dark, almost entirely hydrogen, elegant and completely inert. That's where gravity comes in, the weakest force of all, and at the same time, the only one that never turns off. Each particle in that sea of gas pulled on its neighbors, and the neighbors pulled back, in a motion so slow it was invisible. But the closer the matter got together, the stronger the attraction became. And the cloud began to collapse in on its own center. And compressed gas heats up, for the same reason a tire pump gets hot, on a scale that defies any honest comparison. Gravity squeezed enough matter to form an object 330,000 times heavier than the entire Earth. The temperature at the center of that collapse rose. It went over 100 degrees over 1,000, over 10,000, and it reached 1 million. At some point during this rise, hydrogen stopped being the harmless gas that fills a party balloon. The collisions between the particles became so violent that the atoms were shattered and the electrons were ripped from their orbits. Matter entered the fourth state, the one that almost nobody learns about in school: plasma. A dense and chaotic ocean of bare protons and free electrons crashing into each other at speeds unlike anything in our experience. In this environment, there is no chemistry. No molecule survives even a blink because there isn't a single whole atom left to react. What exists there is brute force physics. The center of the sun today is at 15 million degrees under a pressure that's more than 250 billion times the pressure the air is exerting on your shoulders right now. The material inside is 150 times denser than water, denser than lead, denser than anything you've ever held. And even with all that, the star hits a wall. Gravity wants to bring the protons together. Protons have a positive electric charge, and like charges repel each other. Anyone who has ever played with two magnets with the same poles facing each other knows the feeling. They slip, push, refuse to touch, and the closer you force them together, the stronger the pushback becomes. The same thing happens between two protons, with one cruel difference. The electric force that separates them increases dramatically as the distance decreases. Getting close is easy, but the last steps are the most costly. But there is another force in nature, and it is the most powerful one known. It's the force that holds atomic nuclei together, about 100 times stronger than the electric repulsion. If it were to turn off for an instant, ordinary matter would turn into particle dust. It has a built-in flaw, and that flaw is its range. It only exists at absurdly short distances, something on the order of 1,000th of a trillionth of a meter. Outside that radius, it's zero. It doesn't weaken. It disappears. It disappears.
So the outline of the problem becomes clear. Two protons get close, the electric repulsion increases and pushes them apart. If they overcame that repulsion and reached that minimum distance, the strong force would grab them and fuse them into a single nucleus. In this fusion, part of the mass disappears and turns into radiant energy. And it's this energy that travels through the void and warms your face at noon. Everything relies on overcoming repulsion. This is where the calculation breaks down. To cross that barrier, the protons need to collide at extreme speeds. And particle speed in a plasma has another name. A name you use every day without realizing what it means.
Temperature. When someone says that a pan is hot, what they're really saying is that the particles inside it are moving faster. There is no such substance as heat anywhere. The word describes the agitation, and that's all. So, to know if the sun can fuse protons, you just have to ask at what speed they need to collide. Classical physics answers precisely. It would take a few billion degrees. The core of the sun is at 15 million nanojoule. The star is almost 1,000 times colder than it would need to be. The sun falls short by 3 orders of magnitude, which is far from being a lucky borderline case. Mathematically, it's a refrigerator. According to the laws of heat and motion, the protons at the center of the sun approach each other too slowly. They feel the electric push and bounce back, ricocheting forever like rubber balls against a wall. Fusion should never even begin. The solar system should be a collection of frozen rocks spinning silently around a sphere of dead gas. And yet the sun is shining and the light arrives. The calculation is wrong somewhere, and the place where it's wrong is the most uncomfortable one possible, in our very way of imagining what a particle is. There's an image that hinders more than it helps, and it comes from the textbook. The little ball, the drawing of the proton as a small solid sphere with well-defined edges and a plus sign on top. That little ball doesn't exist. On the atomic scale, matter has no edge, and a proton is not a compact object floating at a point in space. In the deepest description that physics has managed to construct, a particle is a probability wave, a diffuse mist of possible positions. There is no statement that the proton is exactly here. What exists is a very high chance of finding it here, a smaller chance a little further ahead, and a tiny but not zero chance much farther away than any intuition would admit. The particle is smeared out across space, and this does not describe a limitation of our measurement. No better instrument would solve it, because the uncertainty belongs to the particle and not to the device. When this cloud of probability encounters the electric barrier of the other proton, something happens that no tennis ball would ever do against any wall. The wave doesn't just bounce back home, it penetrates the barrier and loses height as it moves inside. If the barrier were infinitely thick, the wave would reach zero, and that would be the end of it. But the barrier has finite thickness, and that's where the hole in reality is. The wave decays, 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 and there's still something left on the other side, an infinitesimal remainder, absurdly small, but different from zero. Translating what this means in the physical world, there is a tiny probability that the proton never needs to climb the barrier. It simply stops being on one side and starts being on the other. It appears on the inside in the territory where the strong force is waiting to fuse it on the spot. The particle goes through a wall that it didn't have enough energy to cross. Not with force and not with speed, with probability. This was named the tunneling effect, and it was described in 1928 by a physicist named Gamow, who was trying to understand why certain heavy nuclei spit out particles that also shouldn't be able to escape. The following year, two other researchers realized that the same mechanism worked the other way around, to go in instead of out, and that this solved the star's problem. By the way, the name is terrible. Tunnel suggests an open path, a dug passage, and there is no passage at all. The barrier remains whole and insurmountable by the rules we use for everything we see. What exists is a particle whose location has never been defined, and that's why it can be found where it wouldn't fit. This is the part that took me the longest to stop mistranslating in my head. For a long time, I imagined the proton pushing, forcing its way, finding a gap. None of that happens, and there's no effort involved at all. A different sentence unlocked it for me. The proton was never fully here to get stuck behind it, but now a new problem appears, and it's as big as the first one. The probability of the proton passing through is so small that it defies comparison. The average waiting time for a proton in the nucleus to fuse with another is billions of years. An individual proton in the densest and hottest place in the solar system spends more time waiting than the Earth has existed.
And here, I disagree with the way this story is usually told. The popular version
Stops here.
It states the sun is slow due to the rare tunneling effect, then shifts to the next topic. That's true, but incomplete. And the part that's left out is actually the most beautiful. When two protons finally meet on the other side of the barrier, they don't form a stable nucleus. Two protons stuck together fall apart almost instantly. For fusion to work, something else needs to happen at the exact moment of the encounter. One of them has to turn into a neutron.
This conversion depends on another force, the weak force, the slowest and most reluctant of the four forces of nature. The two protons meet, stay together for such a short amount of time that it doesn't even have a name, and almost always separate without anything happening. What keeps the sun going is two rare things stacked on top of each other. First, the electric barrier, which is only overcome by probability. Then the weak force, which needs to act within a ridiculously short window of time. And your life depends entirely on this double reluctance, without any rhetorical exaggeration. If either one of the two were just a bit more generous, the sun would have consumed its own hydrogen in a fraction of a second, would have exploded the day it was born, and the cloud of debris would never have formed any planet. The one who put together the entire chain, step by step, was a physicist named Betty in a 1939 article about energy production in stars. He described the reactions one by one with the rates and the energies involved. It's a work of rare clarity, and it took 28 years to earn the highest prize in physics in 1967. With the chain in hand, you can do a calculation that completely changes the image we have of the sun. It's the calculation I mentioned at the beginning. Everyone treats the solar core as the most violent place in the known universe, and it's all true. But the right question is a different one. How much energy does a piece of this core produce per unit of volume? A cubic meter at the center of the sun generates about the same amount of heat as a pile of leaves rotting in a backyard. You didn't misread that sentence. The most extreme place in the solar system produces heat at a rate similar to that of a large lizard sunbathing on a rock. And the next comparison is the one that really got me. The human body burns around 100 units of energy per second to stay alive, distributed across 70 kilograms of flesh. The sun spreads its energy over a much larger mass. When you divide the two sides, each kilogram of your body produces more than 7,000 times more heat than each kilogram of the sun. You are, per kilogram, much hotter than a star, and yet you still need it so you don't freeze, because it has a number of kilograms your imagination can't grasp. That's where the story changes. The sun isn't intense, it's big. The number of protons inside it is a 57-digit number. If the odds of a winning ticket are 1 in a trillion, buying trillions of tickets at every moment guarantees a continuous shower of prizes. The overwhelming majority of protons bounce off uselessly, but there are so many that the absurd minority that make it through can sustain a star for billions of years. Cosmic power made of weakness multiplied by vastness. And this slowness has a practical consequence that shows up in the news from time to time. Fusion reactors on Earth try to produce the same reaction the sun does, but they can't replicate the recipe. The sun makes up for its sluggishness with quantity. Too many protons, too much volume, too much time. A reactor doesn't have any of that. It fits in a warehouse, it operates for seconds, and the fuel inside is millions of times more rarefied than the solar core. So engineering makes up the difference with temperature. These machines operate at around 100 million degrees, more than 6 times the heat of the center of the sun. To reproduce the laziest star you can imagine, it was necessary to build the hottest place in the solar system down here. And this slowness does one more thing, perhaps the most important of all. It keeps the star stable. The sun exists in a balance between gravity pulling everything inward and the energy from fusion pushing everything outward. The two cancel each other out, and the balance corrects itself. If fusion sped up for any reason, the core would heat up, expand, and as it expanded, it would cool down, and fusion would slow back down. The sun is the most reliable thermostat there is, and no one designed it. That's why it doesn't explode. And that's why the temperature on the surface of the Earth has fluctuated within a narrow enough range to allow liquid water for billions of years in a row. There was no kindness in that. There was physics. Now the energy has already been produced in the center, and it still needs to come out. This part is the most unlikely of all. When fusion happens, a photon is born. The particle of light, the fastest thing that the laws of this universe allow. In a vacuum, it travels at 300,000 kilometers per second, and nothing surpasses that. If the sun were hollow, that photon would reach the surface in just over 2 seconds. It would cross the void to Earth in 8 minutes, and that would be the end of it. But the path to the surface is through the densest material the star has, and the photon is born right at the bottom of it. It starts out, moves a tiny fraction of a millimeter, and hits. A free electron absorbs the light, and for a moment the photon ceases to exist. Shortly after, the particle returns the energy as a new photon, and here is the cruelty of the process. The direction of that re-emission is random. The particle doesn't know where the exit is. It has no map, no preference. The new one can go forward, backward, to the side, and there's a good chance it will go in the wrong direction, returning to the center. Physicists call this a random walk. It's the path of someone crossing a crowded stadium in the dark, pushed in a different direction with each bump. The individual speed is extremely high, but the progress toward the door is almost nothing. The result is that the energy generated at the center of the sun takes tens of thousands of years to reach the surface. A particle traveling at the maximum speed allowed by the universe takes millennia to cross the radius of the very star where it was born.
And this is the part that I'm still not sure I fully understand. The numbers that are given for this delay vary in a way that's bothersome. I've read 10,000 years. I've read 170,000. I've seen the estimate of 100,000 that became standard in documentaries. The difference comes from choices about how to model the density of the solar interior. None of these calculations are sloppy, and yet they disagree by a factor of 10. I use 100,000 years out of habit, not out of conviction.
And there's a famous phrase about this that's usually said in a very poetic way, that the light touching your face is 100,000 years old. That's partly true and partly poetry. The photon that arrives here isn't the same one that was born down there, because it was absorbed and re-emitted so many times that the identity of the particle was lost along the way. What traveled all this time was the energy, and that doesn't make the story any less impressive. The energy that warms your skin today was released at the center of the sun at a time when the only existing humans still shared the world with other human species. And this delay serves a second function that almost no one mentions, and it's literally vital. The energy produced by fusion doesn't start as visible light. It starts as gamma radiation, the most destructive form in the spectrum. If it came straight out of the core and traveled in a straight line to here, it would strip the planet's atmosphere and sterilize the entire surface. No cell would survive the afternoon. But with each collision, a microscopic fraction of energy is delivered to the plasma. The gamma radiation degrades and turns into X-rays. It keeps ricocheting for millennia and weakens until it becomes ultraviolet. It bounces a few billion more times and finally emerges at the surface as visible light and heat. The prison is the filter. The same density that delays the energy for tens of thousands of years is what transforms sterilizing jets into midday light. Without this delay, there would be no life here to complain about it. And then, after all that imprisonment, the light travels 150 million kilometers in 8 minutes and 20 seconds without hitting anything. 8 minutes of freedom after millennia of confinement, which is the most unbalanced ratio I know of in any natural process. There's still the final calculation, the one that tells us how much all of this costs. When 4 protons complete the chain and form a helium nucleus, a bookkeeping anomaly occurs. Weighing the 4 protons before and the helium nucleus after, the numbers don't add up. The helium weighs less. About 0.7%, 0.7% of the original mass is no longer there. It didn't hide or leak away. It stopped being matter and turned into energy. Following the most famous equation in physics, the one you see printed on t-shirts, mass and energy are the same thing in different units. And the conversion factor is the speed of light multiplied by itself. 0.7% seems like harmless rounding, but the scale corrects that impression right away. To maintain balance against its own gravity, the sun needs to fuse 600 million tons of hydrogen into helium every second. And in this process, every second, 4 million tons of matter cease to exist. 4 million tons per second erased from physical existence and converted into light. While this sentence is being spoken, the sun has already lost more mass than all of humanity combined has ever had. This has been happening nonstop for 4,600 million years, and we can say where we are in this story. The sun has already consumed about half of the hydrogen in its core. The star is in middle age, and we will be just a blink at the end of the chapter. A skeptical question belongs here, and it's the right question. No one has ever been inside. How do we know that this chain of reactions is what really happens, and not just an elegant story that adds up on paper? The answer is one of the most ingenious things science has ever done. Every time fusion happens, the process also spits out a ghostly particle that hardly interacts with anything. It passes through the entire sun without hitting anything and comes out the other side at the speed of light. While this sentence comes to an end, tens of billions of them have passed through every square centimeter of your skin, day and night, because at night they come through the entire Earth without even noticing it's in the way. These particles are the only thing that comes straight out of the core. Light takes millennia, and they take 2 seconds. They are real-time witnesses to what's happening right now at the center of the star. At the end of the 60s, an American chemist decided to try to capture some. He filled a tank with almost 400,000 liters of dry cleaning fluid and buried it 1.5 kilometers deep at the bottom of a gold mine to block out everything else. The predicted captures were extremely rare, just a few per week, and he had to extract individual atoms from an Olympic-sized pool of liquid to count them. He found 1/3 of what was expected. 2/3 of the particles were missing and remained missing for 33 years. For 33 years, 33 years, there was a real possibility that the entire theory about how the sun works was wrong in some important way, and no one could say what it was. The answer only appeared in 2001 in a Canadian detector built at the bottom of a nickel mine, capable of detecting all 3 types of these particles instead of just one. Nothing was missing. The particles changed type during their journey, oscillating between 3 identities as they travel through space. The old detector could only see one of the 3, so it counted 1/3 of the total. Adding up the 3 types, the number matched the prediction made from the chain described in 1939.
1939.
The theory was right, and it was the instrument that was only seeing 1/3 of the world. I think this story is better than the discovery itself. For 3 decades, the comfortable option would have been to dismiss the measurement and trust the beautiful theory. No one did that. The discrepancy remained unresolved, troubling, and in the literature, until the right instrument came along. And in the end, the anomaly that seemed to threaten solar physics revealed a new property of matter that no one was looking for. And the delay of light and the haste of these particles together produce a consequence that took me a while to grasp. If fusion in the center of the sun stopped now, this very second, nothing would change in the sky. The surface would keep shining exactly the same way for tens of thousands of years.